Hi everyone. Welcome to the 144th Stanford MedAI Group Extend session. This week we have with us Wenqi Shi joining to us to talk about their work on training LLM agents for code-based medical reasoning at scale. Uh, Dr. Wenqi Shi is an assistant professor at the Peter O'Donnell Jr. School of Public Health, UT Southwestern Medical Center. Her research lies at the intersection of AI and healthcare, advancing both fundamental algorithms and applied systems for precision and personalized medicine. Her work has been focused on pediatric healthcare, cancer, and rare diseases. So, Wanki, thank you so much for joining us today. And before we start, do you have any preferences on how you would like to take questions? Do you want to take questions? Do you want people to interrupt you during the course of the talk, or you want to keep the questions till the end of the talk?
Yeah, thank you for your warm introduction. For the questions, I'm flexible with any type of questions. Maybe for like short clarification, this kind of questions, feel free to interrupt me anytime during the presentation. And for those long discussion questions, we can keep it to the end. Yeah.
Okay, awesome. So let's try to make this a session as interactive as possible. And without further ado, let me hand it over to Wanki.
Yeah, thank you so much, and thank you everyone for being here. It's my honor to give a presentation focusing on my recent research, training large language model agents for coding-based medical reasoning. So just to go a little bit about like our long-standing goal in the biomedical field, where we try to build an AI system that can make discoveries like at the scientist level, right? Like today, we're still far away from like a fully autonomous AI scientist, but like recent progress in agent-based AI has already opened a practical way towards that vision. Like the recent studies from like Stanford, for example, like the BioMNE, and also like a lot of good studies before like the virtual lab. Instead of treating a single large language models as all-purpose tools, we can couple language models with machine learning tools, pipelines, the laboratory automation platforms, as well as the human expertise, so that we can get a result of a large language model agent discovery workflow that could reflect the way biologists or clinicians that actually work with the data of many different kinds, like images, sequence, structured data, not just pure text in the language modeling. So let me start like one step back and then show where the agents face. So to design such agents for the biomedical research, we propose like four cooperating modules. Like a large language model could act as the brain of an agent, while the reasoning and planning, the tool use the short-term and long-term memory, as well as the feedback from the body that turns the knowledge into actions are actually important components for a functional large language model agent. So, for example, for the reasoning and planning, right, like the agents could break down a large or complex task into smaller, manageable sub goals and then enable more efficient handling of the complex task. For example, in the React framework, we think and then like act, and then based on the observations, we repeated this iterative reasoning and planning process where the agent could do criticism or self-reflection over the past actions and learn from mistakes and refine them for future steps, thereby improving the quality of the final results. And such planning agents could combine with the chain of thought style inference with the feedback from the simulation or environment that allow the agents to form and test different hypotheses in the biomedical areas and then like rewrite them when the evidence disagrees and then decided to when to ask for a human or like expertise guidance. And also for the tool use, right? Like the agents learns to call external APIs as external tools for extra informations that missing from the existing models, including the concurrent information, including the code execution capability, and get access to different information resources and get access to different like external software database to augment the standard protocols and tool APIs for more reliable way to act. And also for the memory, right? Like we have like short-term memory to keep context from the existing task, while we have long-term memory to store those knowledge like information where we could learn from the representations and past results using different retrieval or model editing or fine-tuning update to reflect the memories, to reflect the knowledge in the memories to help with the next decisions. And then like for the environment feedback, we have both open loop and closed loop systems where like open loop system are cannot act based on the environment feedback because it generate the action steps in the very beginning, while we are value more on the closed loop systems where we use the feedback to continuous correct the agent actions. So these are just like a very brief introduction of like how agents are act with the large language models at their brain, and for the like near term development of such agents, like for example the Google AI co-scientists and different AI agents that are facilitating or like shorten the discovery cycles for experiments can help with flagging those unexpected signals and reuse some previous results. And also, like this kind of scientist could largely accelerate the discovery process. But if we think that in a longer term, right, like this kind of using natural language to reasoning through different inputs and then process the procedures and then reflect back from the environment feedback. It's actually pretty difficult to link multimodal input data, to link multi-source information, to act between different types of tools to perform multi-hop or complex reasoning and to fulfill the requirement of different output requirements, right? So to link those more complex patterns in a more like efficient and standardized and complex and automated way, we think that besides the agent code, besides larger model as the brain of an agent, we think that code is the solution towards more efficient, standardized, complex, and automated way for the biomedical discovery. So, so just to uh, like narrow our like scope from the scientific discovery to the biomedicine to medical reasoning, right? As an audience from this Stanford like MedAI group, this sessions, I think this is a probably the easiest part of this presentation where I try to introduce different coding tasks in medical and biomedical applications. And from past sessions, we see a lot of great work that focuses on the machine learning model development, clinical trial data analysis, the health outcome research, and different even large language models development for different medical applications, right? These tasks, they're actually naturally coding relevant tasks. We naturally solve those tasks by writing a code, by programming to perform or conduct those tasks. That's part of the coding-based medical reasoning for like we use code generations to perform medical reasoning. That's naturally the part of the work. And there is actually another part of the work that they are originally rule-based or even equation-based numerical calculations, or they are not naturally we write code to solve that, but they could potentially benefit from the code-based reasoning, comparing with like rule-based or equation or numerical-based reasoning, where, for example, for some tasks in the Macaque bench where we employ like a risk prediction tools, we can say that by using code as the language, we can see a significant performance improve by by introducing the code as the language to perform the medical reasoning. So that's why we want to focus on the existing code-based reasoning as well as those tasks that could benefit from the code-based medical reasoning. Just to give a proof of concept example, I would to briefly discuss one of our previous works to show that how large language models could actually facilitate the multi-hop reasoning in the medical applications. So, as we know that in the clinical research and practice, clinicians always like interact with the EHR systems to access and retrieve patient data, ranging from like detailed individual level patient records to a more like comprehensive population level of this kind of insights. Like maybe like in Southwestern, in my department, right? Like the clinicians may come to us with their requirement on like I want to have a like access to like this specific sub cohort of patients. Can you help me retrieve from the system? Or I want to know the cost of a specific medicine that like used by a specific group of patients. This kind of complex multi-hop questions that are not available in this existing predefined rule-based conversation system in most EHR system like Epic, right? Like we need to work with the data engineers to write the SQL code to filter and select and get the informations from the maybe SQL database or our existing database, which could lead to inefficiency and delays that may impact the quality and the timeline of the patient care. So alternatively, we think that an autonomous agent could facilitate the clinicians to communicate with EHR in natural language by translating the clinical questions into machine interpretable queries and then planning a sequence of actions as we showed before, and then like ultimately delivering the final responses. So there are several challenges to achieve this goal. Like despite their like success in the general domains, larger models has encountered like some unique and significant challenge in the medical domain, and especially when dealing with the like this complex electoral health record system, which requires advanced reasoning across like a large amount of records within multiple tables. Like for example, in the general domain, the SQL database usually contains like a small scale of records. Note that like our like unit here is actually k rows per tables. Like we can see here, like in the electoral health records database, we have a significant large number of tables as well as a significant large number of records. And more importantly, think about the task we're dealing with in like when we retrieve patient data from electoral health records database, right? It's actually not we can retrieve all the required information from a single table, but we need to transfer between tables, connect different tables to answer one questions. For example, in the general domain, like we for answer per question, we may just need to look at one single table. But like when we answer like actual health records relevant questions, it's likely that we need to connect those drug tables with patient informations, with department informations, with class, with different tables, like converting like two or three or more tables to answer one single questions, which is definitely like a multi-hop tabular reasoning that requires advanced advanced coding capabilities. So that's why we want to translate an EHR question answering problem into a two-use planning process where we could generating and then executing and then debugging and optimizing a sequence of code-based action to enable larger models to conduct complex operations such as like the calculations, like the information retrieval, so that we could integrate the external tools during the interactions with EHRs. So that's the motivations that why we want to like propose like a EHR agent, a large language model based agent for the multi-tabular reasoning. So first we want to overcome the lack of domain knowledge in larger models, and especially when you think of a coding task relevant to electoral health records, right? It's not that the medical knowledge that we want to gain from the literatures, but it's more like the medical knowledge regarding the each single tables, what information are contained in these tables, what informations are contained in this column, what informations are contained in this row, right? So that's why we want to instruct the EHR agent to integrate with the query-specific medical information to being able to effectively reasoning from the given query and locating the query-related tables and records. And secondly, we want to establish an interactive coding mechanism where it includes a multi-turn dialogue between the code planner and executor. It's likely that we cannot write the code that executes correctly in just one time, right? It's likely involves some uh, execution errors, and then uh, we receive those errors information, and then like debug and refine based on the generated code to achieve complex multi-hop reasoning. And also, more importantly, we try to optimize the execution plan by incorporating the environment feedback, not only the error information itself, but also diving into the error messages to locate where the error happens. So instead of I have a code, when I receive the error message, I rewrite everything else. But like we try to dive into the error message to enhance the debugging proficiency. And lastly, we're incorporating the long-term memory to continuously maintain a set of successful cases and dynamically select the most relevant few shot examples to being able to effectively learn for the next questions. So, to give a more like to give a like an example of this workflow, right? Like given input clinical questions with EHRs, EHR agent will initially incorporate the relevant medical information and then like decompose the task into a few code-based plan, call different tools and then like learn from the future examples from the long-term memory with integrated medical knowledge and then execute the code, generate the code and execute the code and iteratively debug based on the error message and ultimately generate the final solutions. We evaluate EHRAgent on three public available structured EHR database, including the Mimic3 and the EICU from the EHR SQL database, as well as the TREQS, the tracks for multi-hop reasoning and question answering on electoral health records. All the questions are originate from the real-world clinical needs and covers a wide range of tabular queries commonly posted in the EHR system. And our final dataset includes an average of like 10 table per dataset, and also around 700 examples per dataset with an average of 1.9. Basically, you need to look at two tables to answer each questions. So definitely like a multi-hop questions. And actually the complexity level here reflect how many tables you need to look at. You need to look at one or two, three, or like more tables to solve one single questions. And when by that time back to 2024, we employed the GP4 as the base language models for our experiments. And then we compare EHRAgent with other like agent scaffolds for like planning to use, including both the reasoning methods that with natural language with natural language without like a code interface to call different tools, as well as the agent methods that with a code interface that try to write a code to solve this kind of questions. And from the readouts, we can observe that like across all the three datasets, EHRAgents are significantly outperform the existing baselines, indicate that the efficacy of our K designs, the interactive coding with the environment feedback, as well as the domain knowledge injections to gradually refine the generated code and then provide the sufficient background information during the planning process. And when we look at the
Wenqi,
yes,
can I ask a question for the
yes,
previous slide?
yeah,
Just wanted to ask, like, you have both successful rate and completion rate matrix over here. Do you account for hallucination or something like that, like when you are generating all these outputs using your LLMs at different stages? Like, do you like what? How do you define your two matrix? That was my question. And if it's like incorrect, say for example, your LLM is hallucinating at one point, do you account for that, or is there a metric that you're going to talk about later on, which accounts for hallucination or something like that? That was my
yeah.
question.
Yeah, this is a good question. Actually, the completion rate means that It's not directly linked with hallucination, but it means that when the larger models being able to generate like a executable code, and the successful rate are actually means that when we execute the generated code, we get the correct results, so that you can say a difference, like you can say the gap between the successful rate and the completion rate. This actually reflects a kind of hallucination in like we generate like large model generate the executable code, but actually are not get the correct results. And we actually have like an error analysis back in our paper to show that how the potential like errors or hallucinations are looked at.
Just following up on that, in this scenario, is there any concept of like a partially correct code or like partially correct answer,
Uh,
or
because
it's just like have to be perfect for you to count it towards completion or success?
it needs to be perfectly or strictly matched with the final results. Yeah,
Okay.
because all the questions are like are actually you can actually as a data engineers to write the SQL code to get the final results. So every single values are actually verifiable. There is no partially correct, right?
Okay. Perfect.
Mhm. Yeah, thank you for your good questions. And just to continue on the ablation study as well as the effect of different components in EHRAgent, we can definitely say that the interactive coding are the most significant contributor across all the complexity levels, which highlight the importance of the code generation in the planning as well as the environment feedback, the error message to provide the guidance for the refinement. And also when we take a look at the model performance by considering the different dimensions, different dimension measurements of the question complexity, including like including the how many including the different level of the difficulties, we can say that the EHRAgent are consistently outperforms all the baselines at various level of difficulty. And also we can say that comparing with the previous text to SQL or like EHR to SQL supervised learning settings where we need around like 10K samples with detailed annotations. Here, the detailed annotations mean that like for each question you need to pair with code snaps, right? And the EHRAgent are actually enable more like complex tabular reasoning with only like around four demonstrations. So these are like a work as a proof of concept for our like how to use code as a language to facilitate the larger model agents in different medical applications. However, if remember that we use the base model as GPT-4 as the backbone language model to generate the code. However, if you change the model to like a less capable model like GPT-3.5, we can see a significant like performance drop, even though like EHRAgent still outperforms other baselines, but we can see a significant performance drop by just changing the backbone models. So this show that larger model EHRAgents, this kind of prompting based uh, agent scaffold. It adapts larger models to EHR tasks, but not fundamentally improve the code generation capabilities in larger models. So existing coding-based agents are like rely primarily on this kind of prompt engineering without the systematical improvement. This could limit their like robustness and scalability when addressing more complex or diverse coding tasks in the real-world biomedical scenarios. So that's why to solve these limitations, we want to shift our focus
Wenqi,
to the. Oh
sorry,
yes,
sorry to interrupt. We have one question from the
yes.
audience.
Mhm.
So, which laws did you use for training or fine-tuning the LLM, and how is it related to the perfect match considered for your successful rate in the model evaluation?
Oh, for the EHRAgent is purely prompt based without any training. Like we only use for few shot demonstrations as like a few shot exemplars.
Okay. So you use basically like in context learning or something like that.
Yes, in context learning,
Yeah.
yes.
Thank you. Thank you so
Thank you.
much.
Yeah. And yeah, that's a good question actually, linked to our like training agent here. So as we mentioned before, we want to systematically improve the coding capabilities for like larger model agents. So that's why we developed like the MedAgentGym. To our knowledge, is one of the first public available release training environment that targets the coding-based medical reasoning in large language model agents. Like it's actually Unix rigorous and comprehensive benchmark for math coding evaluation with expandable training resources that are running inside with a one containerized execution layers. So this combination of benchmark as well as the training environment hope to allow the researchers to build and train and assess the larger model powered coding assistant to support advanced biomedical investigations and clinical practice. And to avoid potential confusion here, sometimes I mention it as like medical coding, but here like we really focus on the computational code generation for medical reasoning, rather than the traditional medical coding system where we say like the SD9 or SD10 code. So, just to go a little bit of existing medical reasoning dataset and benchmarks, this table summarizes the like many widely used. I believe most of you are familiar with them, like MedQA, MedSQA, this PubMedQA, this QA rated dataset, which primarily assess large model performance through the closed-formed medical QA tasks. And despite this extensive like benchmark efforts, existing benchmark even focus on code like EHRSQL or like MedAgentBench or BioCoders kind of data set for coding for a specific or target domain. It with limited emphasis on a dedicated training environment. It more focus on provide a evaluation, but not focusing on aim at systematically improving the coding and medical reasoning capabilities, especially for those coding intensive and interactive medical scenario. So, in that regards, MedAgentGym wants to target a comprehensive suite of reasoning-intensive coding tasks, and also introducing a like a unified and scalable and interactive training environment to systematically improve the coding-based medical reasoning capability of large language models. So first, let's go through the collection of coding instance we included in the MedAgentGym. So we have around 72K coding instance across around 129 categories grounded in the real-world biomedical scenarios. The task actually span from structured medical information retrieval to numerical medical reasoning to bioinformatics modeling as well as machine learning tasks, and I want to introduce them one by one. So the first category of task is like what we discuss in EHRAgent is the EHR to SQL style questions, where we try to generate SQL queries that reflect a wide range of needs in the hospitals, including patient information retrieval, operations like calculating the survival rate to understand the various time expressions to answer those time-intensive questions by interacting with the EHR systems. That's like a standardized database query. This kind of questions includes around 5 relevant datasets. And then the next type of questions are regarding to biomedical data science, such as the MedCock bench, for example, where we want to evaluate the qualitative capabilities of the medical large model agents in the real world scenario. For example, the doctors frequently use those risk calculators or clinical calculators that follows a specific like quantitative equations or some rule-based reasoning paradigms for those evidence-based decision support. Like MedCock benchmark contains an evaluation set of around 1,000 manually reviewed cases from different, I think around 55 like different medical calculators. And such tasks are composed of a patient note, a question regarding this medical values, as well as medical like calculators to generate the ground truth answer. And you see here we include this kind of like the previous database tasks, they are like naturally coding-based task, right? And the task like the markup bench, they're originally not a coding task, but since it has a verifiable answers, it could be benefit from the coding. So that's why we also include such not originally a coding task, but could benefit as a coding task here in our comprehensive benchmark. And the third type of task are more open-ended bioinformatics tasks that when we're dealing with diverse data types like genomics and clinical data types. For example, in BioDS Bench and BioCoder, BioDS Bench is more like you try to reproduce like analysis, visualizations, data analysis from like a paper or a literature. It contains around 300 coding tasks performed on real-world TCGA type of genomics and clinical data. And the last categories of tasks you may be more familiar with, like the machine learning development task, where like for example, for the like this is another good resources from Stanford, like the EHRagent, right, contains the identified structured data from the EHRs of around 6,000 patients from Stanford Medicine, where had contains 15 different prediction tasks, including the operation outcomes prediction, diagnosis, image findings, as well as the lab test results, which contains multitask, like multi-class classification. So these are just like a category, like four different large categories of computational tasks we structured with MedAgentGym, like for each, like how to standardize the task from different like sources to a unified benchmark, right? Like we want the EHRaGent, the task in EHRaGent are structured with first the problem description, and secondly, a verifiable ground truth output, and thirdly, they potentially not required, but potential for some EHR related task, right? They need the original data resources. So, and also for coding centric tasks that only provide the reference code implementations. For example, for like BioCoder, they are originally like a coding task. So their ground truth solutions are actually like a code snaps instead of a single value. We need to transform this code into a like a successful into a definitive like outcome signatures, which means that we need to generate the outcomes of the code as a verifiable results, because you can have like multiple different formats, different kind of code that lead to a only single reliable results. So that's why we need a verifiable results as the final answers instead of the code itself. And also for tasks that involving the different data resources, we include the like EHRagent includes the EHR data, the EHR SQL, the mimic3. Yes, you include those EHR data. We include the metadata on the data access and sources for the larger model agent to get access to those data. Like MedAgentGym, as we described, like we need the question description, the verifiable ground truth output, as well as the data resources. MedAgentGym is actually a pretty flexible and easy accommodating any new task that has clear descriptions, verifiable ground truth outcomes to be integrated into the gym style environment. And also, clinically, we prioritize those tasks that are originating from the real world healthcare settings, like EHRsql. They are like mimic3 and ESU. They're all from the real world patient data and verified by the human programmers or the human expert. And computationally, we try to integrate diverse type of biomedical coding tasks, including those structured medical information retrieval tasks like the database query, like when we use the tools in the markup bench, as well as more open-ended question, right? Like when you reproduce results in a paper, like in the BioDS bench, the answers could be the questions and answers are not have like a template for that. So, to summarize, a MedAgentGym is a unified training environment that built upon a large scale and high quality data set that's comprising around 72K task instance from these 12 real world biomedical scenarios. And with MedAgentGym, we will be able to collect a large-scale agent trajectories to support the agent training. So that's why we not only provide a comprehensive suite of benchmark evaluation, but also provide a training environment to accommodate the diverse research need. And also, considering the computational resources and training efforts, we also provide a leaderboard, like a subset of our current training environment, which is a balanced and a lightweight subset for efficient leaderboard training and evaluation to being able to use if you have a smaller scale computational resources or limited budget in the API function call. So we then extensively benchmark the existing SOTA large models and reasoning models and domain-specific domain-specific models that are available in the current settings. Note that for the commercialized larger models, we only focus on the Microsoft Azure, the GPT series models because of the data usage agreements, like in Mimic 3 and in different data resources. Only Microsoft Azure, this kind of resources are like OpenAI API resources are compatible with their data usage agreement. But still, we can say a significant performance gap between the commercialized large models versus those open source small language model, including the most recent, the Q13 series, right? Like we can see a significant gap between the commercial model versus the small open source model, and this highlight the critical need why we want to build an environment for continued development of those lightweight open source models that could match the commercial performance, while also addressing those real world privacy and cost constraints. And also, when we look at those structured questions, like in the database structures as well as the MedCoc, versus those open-ended questions that in like MedAgent bench, the bulk coder, bulk DS bench, and the EHRagent. Like we can say still we have a higher performance on those structured EHR query based questions versus like a little bit like the open-ended bioinformatics queries are remain challenging, right? And also we can see definitely like a significant performance gain with those reasoning based models. We have reasoning models here, uh we have like the QW32B as well as the DeepSeek R1 series model. We can see a significant performance boost with those reasoning capabilities. And interestingly, when we look at the domain-specific model, right, like either models that are dedicated to coding, like the Q1 2.5 coder series model, or medical reasoning models like the most recent, the MedJamma, as well as the Huatuo M1, the MedReason, this kind of Baichuan, this kind of medical reasoning domain-specific models. They are all like perform suboptimal readouts comparing with general domain models or comparing with general models, which is pretty surprising, but also reviewing that code-based medical reasoning are not like a domain or a capability that captured by either coding or medical reasoning domain-specific mode but unique capabilities as a coding-based medical reasoning that needs further training with both capabilities. And
The question, sorry, thank you.
yes,
The question. So you are kind of like if you go back to the last table, yeah, you're kind of reevaluating all these state-of-the-art LLMs on their reasoning capabilities, right? For example, on the MedAgentGym, right?
yes.
So if I understand correctly, so you also might have some gold standard reasons or explanations for each of the tasks.
Yes, we have like for each single task,
Okay.
like the task in the EHRAgent, right? We have specific verifiable answers
Yeah.
so that
And
represent.
verifiable answers as well as I think reasons as well, right? Like, okay, this is the answer that is being selected, and this is the reason that's supporting that answer.
No,
Because
that
okay,
like all the tasks in our dataset are conformed by coding. So basically, you need to write a code to solve the task to reflect the reasoning capabilities.
Okay. Okay. And I mean, the other thing was that, like, when all these models, they usually tend to generate a lot of free text. So how are you kind of doing that? Like, are you looking at partial overlaps, or are you looking at, like, exact matches of the codes that are generated? I was just a little bit curious, like, how the outputs of these models are, and how you're kind of correlating with your, gold standard. That was my question.
Yes,
Yeah.
so basically we force the models to generate the code and then we execute the code to generate the final answers. Yeah. And actually they because our like as a gym environment I will discuss in the future, we also enable the execution and debug in the environment so that when the large model generate a code, it's actually execute and then like with the environment feedback with the error messages, it has the chance to debug over iterations and then generate the final answers.
Okay. Okay.
And just wondering, like in terms of what kind of tables it has access to, are like the free text tables, like clinical notes included in that, or it has to be more structured than this?
In this, it really depends on task. So
Mm.
for EHR related task, for example, the EHR query, they are structured tabular data. And for some other tasks that they're like in general just free task. They don't need metadata.
So, uh, I mean,
For
ideally
for the
these,
data
yeah,
access, it's
yeah, ideally
structured.
these
It's
models would be
structured.
able to, sorry, ideally these models would be able to search through clinical notes or radiology pathology reports for certain characteristics. Are there
Uh,
any of the
we focus on more on tabular data instead
tabular
of
data yet? Okay, okay, makes
Yeah.
sense. Thank you.
that's tabular data.
I think we have a
But this,
question from the audience.
yes.
So, do you compare the generated and the ground truth code, or the output of the codes? Like, he's asking because there can be different versions, different correct versions of a particular code.
Yes, so that's why we only compare the executable result the final results, right? Like you can definitely generate different versions of code, different types of code. That's fine. As long as you get the correct results, then like we can verify that you successfully conduct this task. So you don't need to be correct line by line. Yeah. Yeah, and then like what? Sorry, once we have a once we have the comprehensive suite of coding-based medical reasoning tasks, we have evaluate and benchmark the existing learner models. We see the gap between the open source and the commercialized learner models, and then we are thinking of like how we could improve the learner models for coding-based medical reasoning. And think about that. You train a medical reasoning model, right? You're not only sharing the question and the answer itself, but also you share the reasoning trajectories, like the chain of thoughts, so that the models could learn from the reasoning trajectories. It's similar in the medical, like coding-based medical reasoning, where you thinking trajectory here are actually the coding trajectories. And we expect the agents to first perform like a behavior cloning from the previous expert trajectories, and then interact with the environment to evolve themselves, just like the way that humans learn and develop. And the question here will be how we get those trajectories right, how we get the trajectories to interact with the environment, how we get the generate code and then debug this kind of interactions from the environment, right? So that's why we need a gym-like environment to get those coding trajectories, including the reflection to the environment feedback, so that we can use to train an agent. We need not only the a single copy of the successfully execute code, but we also need the failure cases to help the model learn from those coding trajectories. And this motivates us to transform from a static benchmark, as we showed before, to a more interactive interface. And specifically for each task, we provide an isolated and executable environment in a Docker image where we try to ensure the robust and reproducible coding-based medical reading that could successfully execute using different Docker containers. So why we need such containers? There are two reasons. First, like for example, for some task you got a bug, like I cannot execute it because I lack of some access to some package. Then you need the terminal access to install some package, right? We don't know if without a Docker environment, you may need install some package into your main system. We don't want that happens. We want to maintain this environment integrated. So that's why we need a Docker environment, not only for the successful execution, but also for the safety of your computer, as well as like for the medical data security, because many of our data are from different like data usage agreements. So we want to safeguarding those sensitive patient information within the isolated Docker environment. And the other features we want to highlight would be the interactive feedback, as we briefly mentioned before, right? Like the MedAgentGym incorporates the same interactive feedback mechanism like what we did in the EHRAgent. We try to effectively bridging the language models with the coding interpreters so that the agent could be able to debug and error grounding based on different error messages and then refine their code. So this is like how the environments look like. And remember that we need to sample such coding trajectories to help train those larger model agent in coding tasks. So that's why we want to each task in the medical agent gym are packaged in a reproducible Docker image to facilitate the efficient trajectory collection. And more importantly, we have built-in support for multi-threading, the parallel execution, as well as the sequential sampling. And we also support the two widely used multi-threading backend engines like Ray and also the job lab to accelerate the trajectory sampling. And this infrastructure actually ensures the efficient and the scalable trajectory collection to supporting both extensive experiment and also the systematic evaluation over different scenarios. And also we want our environment to be plug and play, like where you have a task, you may not have like we mentioned before, right? We have a task, we have the ground truth answer, but we don't really have the code. How do we dealing with that? This environment helps you to generate both positive samples where like you execute the code and get the ground truth answer, as well as the failure cases, the negative samples trajectories where fail the task, so that you could collect a comprehensive set of trajectories to support different training tasks. And also, we define four primary action types, including the request information, where you try to retrieve relevant data from the sources such as EHR if your task needs such data. And also, you have access to terminal, where you can manage your dependency and local files with an isolated Docker environment. If you lack or conflict with some package, you could just reinstall or install some package you want. And also, you have the code execution, just for execute the code and get the answer with an integrated interpreter. And you have the debug function where you can translate the code execution errors into a natural language explanations and enriched with the detailed error information for larger model to comprehensively understanding your error and better debug. And this is like a case study or like an example of how the trajectories look like. It contains not only the original code, but also the error message as the observations from the environment, as well as the debug and the different tasks, the debug process, as well as the final successfully executed code as the trajectories. And we benchmark two different training methods, including the supervised fine-tuning and also the DPO for training on those trajectories we sampled. And we can see that definitely warm-up the DPO, which means like we first SFT and then like follow up with the DPO achieve the best performance. to reflect those trajectories on the coding-based medical reasoning tasks. And also we release all 6K expert trajectories that we sampled from our environment for accelerate agent training. And you can sample and sample more for your own task based on our environment. And also, we show that we could build a verifier to evaluate and judge the quality of the trajectory to support more advanced R training methods like PPO. And also here, like if you see the training times, the train time scaling, right? You can see that this is a result within our leaderboard training data, but we provide definitely more training data than that. So this shows an upper bound of our current training resources and budget limits. But definitely with EHRAgent, even with the current training samples, you may sample more data and it still shows a stable improvement with more training data involved. And lastly, we explore the large model agent scaling with the self-improvement, right? Like we employ the rejection sampling fine-tuning with around 4K trajectory pairs and perform an iterative DPO where we can say that the rejection sampling SFT plus the iterative DPO that you learn from your last checkpoint, like basically a 2 round of DPO, provides another extra performance boost around 3 to 5%. And also, if we look at the debug, like if we look at this some additional like side experiments, right? Like when we look at the effect of the debugging mechanism, where we can say that if we remove the debugging mechanism, we can see a clearly performance drop, which indicates that why we need an interactive environment, why we need such training of not only the successful case, but also the debugging, the environment feedback to improve the agent performance in coding task. And also we can say that we conduct an error analysis here, and we see that still most of these errors happens in stuck in the loop, where after round of debugging, it's not successfully debugged and then end at the like around 15 round of debugging process. And lastly, it's interestingly we see that if you remember that in EHRAgent we provide a few tool sets, including the calculators, including the datetime, to the large model agents, to allow them to use different tools. But surprisingly, we notice that if we don't provide those tools, we just ask the large models to write the functions themselves. It's actually achieve better performance than we constrain the A2 different external tool size. So this is actually like aligned with many existing observations in other papers from Princeton and other like universities, which may need further explorations to more complex tasks and complex tools, because the current tools are obviously quite simple to work as a functions, but may in such case that we think that if we enable the flexible writing, like large model to flexible writing functions, may performs better than when we integrate it with external tools. And also we perform human studies with some graduate level engineers, and we definitely show that comparing with the structured task like the information retrieval task, open-ended tasks are more complicated with less successful rate and like longer execution and longer performance time. So that means like our the task within our data set remains challenging for both human programmers as well as the large model agents. And more importantly, we provide a highly diverse external, like challenging external evaluation test, where it's completely like different from the in-distribution coding task, and to further challenging the large model agents on generalizing to different coding-based medical reasoning tasks. And in summary, MedAgentGym fills a like important gap in the developing the medical coding agents by offering not only a comprehensive benchmark but also a task risk environment that tailored to different demands of the healthcare applications, and also by combining this diverse real-world biomedical task as well as an efficient and reproducible infrastructure, and also this large-scale benchmarking across different language models. We hope that MedAgentGym could provide a foundation for advancing language model agents in coding towards different medical applications. And we hope that with MedAgentGym, it could force the progress in building the efficient and reliable and clinically grounded AI agents to support the real-world research and the practice in healthcare. So if we look back into the systematic review of a large model agent, right, we want the large models functions as the agent brain, but we also want the code could be function as the agent language to accelerate the biomedicine discovery. Yeah, thank you for listening, and I appreciate your attention and questions. And I also welcome to any further questions and discussing on the external platform or collaborating on any downstream tasks. Yeah, thank you for listening.
Thank you so much, Venki. And before we open up the floor for further questioning, I would like our audience to extend a nice round of applause, virtual round of applause. And yeah, so questions.
I see a question from the chat where action items for this meeting is to release our
I
6K.
think that's just from somebody with the Fireflies AI notable.
Oh, okay. I just
Yeah,
want
I
to
think
highlight
this
that.
is kind of summarized your
Oh,
something.
okay.
Yeah.
Gotcha.
Maybe not a
Yeah, yeah.
question.
So the trajectory has already been released on GitHub and also the Hugging Face where you can directly download from online. Yeah, away for the open source, the environment as well as the trajectories.
I think I can start with a question. It's more of like, where do you see this work expanding to? Because I think this question is kind of based on my experience with. It's one thing to be able to work with the tabular structured data. That's one level of complexity. But when you add the free text to it, the complexity level just exponentially increases. So I'm just wondering, do you think like this line of research that you've been doing, would it go on to include those kind of tasks?
Yeah, this is a really good question. So, like, I want to first answering the first question, right? When to extend the task from structured tabular data to more free like free text or like even multimodal data like image data. And actually, we're connecting that, and part of our like resources, if you noted that the EHRagent that data set are actually contains additional image related data set. So I think they even pair with different data resources, the task structure in MedAgentGym is not changed, right? You still need a question description, you still need verifiable answers, but like the different modality of data is basically the third component where either you have a EHR data or you have free text or you have medical image as the metadata resources you need to gain access to. It didn't change the task or the instant structure in this entire process. But the problem is for many free text data, you may have the, for example, for summarization or for image task, like for image segmentation or for those image generation task or like those, the problem may happens when you get a free text of output where your outcome is not verifiable anymore. Then I think that's the next step, how to include the free text output into this gym environment. I guess the solution will be still you have a verifier to evaluate the quality of your output so that you will be able to integrate different task tab, including the free task image, more additional modalities into the environment. And the second question regarding how to integrate this this into like a real world applications into real world scenarios. I have some slides I'm hiding, but like I can briefly show here. So basically, we're actually try to integrate the like coding-based medical agent as a like a co-pilot to connect our like different data commons with different analysis tools. If you think of our current system, right, the data are actually pretty absent from the tools. The data are stored there and you develop tools, they are separate. You can as a if you're not expert in coding, you don't know how to apply those tools on the data. And what we're building as a coding assistant here are trying to bridge this gap. Let's say if you have like a new data coming in, we'll be able to help you easily integrate into the existing data commons. If you have a new tools coming in, you can easily wrap it up with the existing tool set. And similarly, when you have downstream task, when you want to like have a query for like EHRAgent, when you want to build a sub cohort, you want to query for specific data, you can use the code. You can like use natural language to describe your query and use the code assistant to help you with the information cohort definition or information extraction. And the similar for two applications. When you have previous unseen data, you can easily use large model, this kind of coding assistant, to adapt to unseen tools by iteratively debugging some potential errors, right? The data format, the two input output, the package compliance by debugging to solve those problems. So here we try to like bridge the gap between the researchers that needs code to solve different data related questions, solve different tool related questions to accelerate this kind of process by developing a coding assistant to facilitate those natural language queries to being translated to code to execute and get the final answers. Yeah.
Thank you very much. Yeah, I think it's you kind of probably thought of all of the possible ways you can extend this one. So that's very interesting. Only the structured tabular data versus the free text or the imaging data, the processing part, the data processing part or the data integration part, I think it will be like heavily reliant on having some sort of a feature extractor, which might not be very important if you are already dealing with the tabular data. But yeah, the way things are progressing with LLMs and VLMs, I think we're going to get better and better feature extractors anyway. So this is very interesting. Thank you, Wenqi.
Thank you. Yeah, this is definitely our next step.
Okay. Thank you so much. If there are no more questions, we would again like our audience to extend another round of virtual applause. And with that, we can end our session. Thank you so much, Wenqi, for giving such a nice and wonderful talk.
Thank you for having me here.